Now for part 14. Welcome back, ladies and gentlemen, for another episode of the characteristics of inverse function. In this video, 2-in-1, taking care of composition identity and undoing operations. Again, we'll do a proof and then example. We're excited about the entire series, right to the principal nth root. But we're especially excited about this video because we're proving a theorem, but a specific type known as an identity. Because like theorems, identities are proven mathematical statements that hold universally within their domain. However, identities are distinguished by their fundamental, universally true nature. Think of it as a theorem that is always true, not just under specific conditions, like the Pythagorean theorem, which only applies to right triangles. Generally speaking, the composition identity, more specifically, we plan to prove the composite function identity for inverses, which states the inverse of a composition of two functions, specifically f circle g inverse, is equal to the composition of their inverses in the reverse order, which is g inverse circle f inverse. We start by defining two functions, a function g where a maps to b, and a function f where b maps to c. And the second blue bullet defines two composite functions, a function f circle g where a maps to c, and a function f circle g inverse where c maps to a. But before we get into the proof, we'd like to briefly discuss the significance of the composite function identity for inverses. At the same time, the discussion explains why the two mentioned characteristics are being discussed in the same video. The significance lies in the fundamental mathematical principle that to reverse a sequence of operations, which means undoing operations, one must perform the inverse operations in the reverse order of their original application, which is formally defined by the composite function identity, which we plan to show. So basically, this identity will capture the intuitive, undoing nature of inverse functions in mathematical terms, and the composite function identity for inverses is simply reversing or undoing a two-step process, which requires applying the inverse operations in the opposite sequence from the original application. For the proof, we'll also refer to the definition of an inverse function from the previous video. To save space and our eyes, we won't write it. Recall, in simple terms, the definition says, if a function f takes an input x and produces an output y, then the inverse function f inverse must take the output y and produce the original input x. So the identity describes the rule for finding the inverse of a composite function. The formula, the white box, read as f circle g inverse equals g inverse circle f inverse. Here's a breakdown on how it's applied. In the original composite function, f circle g, an input x goes into the inner function g first, the output g of x goes into the outer function f second, yields f of g of x. To reverse this process, we have to find f circle g inverse, which means we must undo the operations in the opposite order of what we just said. We must reverse f first using f inverse. Next, we must reverse g second using g inverse. The notation for applying f inverse first, then g inverse second, is g inverse circle f inverse of y, blue box. The input y goes into f inverse first, f inverse of y goes into g inverse second, yielding g inverse of f inverse of y blue box, bottom right. The blue box correctly reverses the order of operations performed by F circle G, ensuring the original input value is recovered. Is this true? In a quick study, let's see if it is. Sliding over the blackboard, we have the function G and its inverse and their mappings. The same for the function F. In the yellow box, A is an element of set A. What does the composite function F circle G return? The input A goes into the function G first. The result G of A goes into F second, yielding F of B, which equals C. Because G of A yields B, then F of B yields C. Next we have C is an element of set C. What does the composite function F circle G inverse return? The input C goes into the function F inverse first. The result F inverse of C goes into G second, yielding G inverse of B, which equals A. Because F inverse of C yields B, then G inverse of B yields A. The quick study shows, indeed, the blue box correctly reverses the order of operations performed by F circle G, ensuring the original input value, in this case A, from the set capital A, is recovered. Nice. Now let's get back to the proof. We want to prove the white box by showing when we compose the two functions, we get the identity function on both sides, because a function composed with its inverse will always return the identity function. So, to demonstrate that a function h is the inverse of k, we verify two conditions using function composition. First condition, k circle h returns the identity function. Second condition, h circle k returns the identity function. If we let k equal f circle g and h equal g inverse circle f inverse, starting with the blue box, we have f circle g inverse circle f inverse equals the identity function. There's two things happening for this proof. The first, we're referring to the definition of the inverse function, which we already said, and its natural extension. So here's a brief discussion about the composition property of inverse functions. If f and f inverse are true inverses, then applying the inverse function to the output of the original function returns the original input. Number one, the function f takes an element x from set x and maps it to an element y in set y. Number two, the inverse function f takes that element y from set y and maps it back to the original element in set x. Third blue bullet, when we compose these functions, we get f of f inverse of y. Then, applying the definition of an inverse, f inverse of y returns the original input x. It naturally follows we get f of x, which just equals y, which means the composite function returns the original element from the codomain y. Take a look. All we're doing is substituting the input in number 1 with the left-hand side of 2. We can rewrite it as the following: f circle f inverse equals the identity function on the set y. Last blue bullet. Now consider the function composition f inverse of f of x. Then we apply the relation f of x equals y. Next, we apply the definition of an inverse function. F inverse of y returns the original input x. Take a look. All we're doing is substituting the input in number 2 with the left-hand side of 1, which means the composite function returns the original element from the domain x. We can rewrite it as the following: f inverse circle f equals the identity function on the set x, which means while the inverse function returns the original any input x, whereas the composition of a function and its inverse returns the identity function. This relationship is known as the composition property of inverse functions, a defining characteristic of an inverse function where the inverse function undoes the action of the original function, with the net effect being the identity function, which leaves the input unchanged. To start, we'd like to prove the first composition in the blue box. First orange bullet, we use the associative property of function composition. We rearrange the parentheses. Next, we apply the composition property. We have G circle G inverse returns the identity function capital I. We get F circle capital I circle F inverse. Some brief scratch work. If we compose a function f with the identity function from the domain, the identity function acts on the input, which then produces the original output of f. Then we just get f of the identity function from the domain equals f of x. Next, the yellow box. If we compose the identity function with another function f, results in the identity function first acting on the output of f, which again leaves the output unchanged. To clarify, when we compose the identity function with another function f, the identity function acts on the entire output of f of x, because the definition of the identity function, it returns whatever input it receives unchanged. For example, the identity composed with y just equals y for any input y. Just consider the composition. Identity of f of x, so the input to the identity function is the output of f of x, which we can call y. Therefore, we have the yellow box, read as identity of f of x equals identity of y, which equals y, or equals f of x. In our case, the last blue bullet, we have f circle identity, which just equals f. Then we apply what we just said. Yellow arrow to the yellow brackets gives the third orange bullet, f circle f inverse, which we know from the composition property just equals the blue box. Last orange bullet, which matches with the blue box 1. The next goal is to prove the second composition. For that, we have h circle k equals the identity function capital I. We want to prove blue box 2, G inverse circle F inverse circle F circle G equals the identity function. Proving the second composition will be a lot easier, as all the discussions are done. First orange bullet. We apply all the properties that proved the first composition to prove the second composition, beginning with the associative property of function composition, rearranging the parentheses. Next, we apply the composition property. We have f inverse circle f returns the identity function capital I. We get G inverse circle capital I circle G, which just simplifies to G inverse circle G. See that? Last bullet. What we just said just equals capital I, the identity function, which matches blue box 2 nice. Since the composition of a function and its inverse only results in the identity function, and both compositions result in capital I, therefore, the composite function identity in the white box is proven. We are done. Very nice. Let's see the identity in action. Do an example, shall we? The composite function identity is often illustrated by the socks and shoes analogy. To reverse a sequence of operations, you must undo each operation in the reverse order of how they were applied, like actually taking off our shoes and socks. We saw that before, but let's look at it differently. Let's test out the analogy, letting socks equal S and shoes equals H. First though, we need to put on socks, then shoes. First operation, put on socks. Second operation, put on our shoes over our socks. The combined function read as h of s of x, where the input x is our bare feet. To reverse the process, we can't take our socks off first. Reverse operation 1, take off our shoes using h inverse. Next, reverse operation 2, take off our socks using s inverse. To reflect what we just said, the orange bullet. Consequently, the inverse of h of s of x, written as s inverse of h inverse of x. On to the example. Second orange bullet. Consider the two linear functions, f of x equals 2x and g of x equals x plus 5. Let's find the composite function f of g of x. We have f of x plus 5, which equals 2x plus 10. Now let's find the inverse of the composite function. To reverse, 2x plus 10 replace x with y, then subtract 10 from both sides. Second column, divide 2 from both sides, returns y equals x minus 10 over 2. Then replace y with f of g inverse. Then we rewrite the right side equals 1 over 2x minus 5. Next we find the inverses of the individual functions from the yellow box. First column we do the same as before, replace x with y, then solve for y algebraically. Then replace y with the inverse notation. So we get f inverse of x equals x over 2. We also have g inverse of x equals x minus 5. Almost done. We compose the functions in reverse order. Second column, we have g inverse of f inverse of x equals g inverse of x over 2. Then we replace every x in g inverse with x over 2 to get x over 2 minus 5, which just equals 1 over 2x minus 5. Since the result from the previous step is identical to the last result, the red boxes match. This again confirms the identity in the large red box. The identity ensures that the inverse of the composite function is correctly defined as the composition of the inverses in the correct reverse sequence. But what about the compositions of the function and its inverse? Here we can do some mental math. First, replace every instance of x in f circle g with 1 over 2x minus 5. 2 times a half essentially simplifies to 1, which just leaves x minus 10 plus 10, which just equals x, the identity function. Next, replace every instance of x in f circle g inverse with 2x plus 10. A half times 2 simplifies to 1, and a half times 10 returns 5, which just leaves x plus 5 minus 5, which, as expected, just equals x, capital I. Thus, this identity confirms that applying a function f and then its inverse or vice versa has no net effect, returning the original input value. This round-trip effect is exactly what is expressed by the composite function identity. This is the fundamental definition of an inverse function. So we're putting some extra energy, time in this video for the viewers, but also for our own understanding. To conclude, this video study is really a culmination of the previous work, as the identity highlights the relationship between the domain and range of a function and its inverse. Because the domain of f is the range of f inverse, and the range of f is the domain of f inverse. The composite identities ensure the inputs and outputs align correctly across these domains and ranges. In simpler terms, if a system uses composite identities correctly, every input generated by the forward function is a valid input for the inverse function, and the combination brings you back to the exact starting point. This study is also part of our mission, found in our description, as the concept of the inverse is a foundation of advanced mathematics. It's not merely an algebraic tool, but a core structural principle that enables us to solve equations involving functions and their inverses. For example, in a previous video, we solved a nonlinear equation using the inverse of e to x, ln x combined with the Lambert W function, which is an inverse, although it's a special function needed to solve equations involving exponential form. Special meaning it's the idea of an inverse, but for a function that doesn't have a simple algebraic inverse, requiring a new named function w to express the solution. We'll see if we can put it up on all channels. In essence, the composite function identity is the core concept that establishes the unique relationship between a function and its inverse. They are perfect opposites in terms of their operations. It takes the conceptual idea of a process and its reversal and translates it into a precise, verifiable equation that holds true for all possible inputs, making the intuition mathematically rigorous.